The most common security breaches take place due to the most straightforward security measures being missed. PSA Certified has been developed to help create a foundation of trust for all connected devices and make this as easy as possible to prevent security attacks. PSA Certified builds upon best practices from across the industry and is aimed at the various entities throughout the supply chain, from chip designers, software vendors and device developers to cloud and network infrastructure providers. Though the focus is on locally networked or internet-connected devices, many aspects are also relevant for non-connected devices. Regardless of the application an IoT device is used for, and whether it is large or small, there are common foundational goals needed to be achieved to secure a device on a network. These are not just specified or restricted to the device. They span the device's requirements, the cloud, how they communicate, and how a user uses a device. PSA Certified defines 10 core security goals devised to guide security best practice and provide a practical checklist to follow. These 10 goals, which we look at in this module, provide a high-level abstract way to think about the essential features necessary to secure and establish trust. Every product has unique functional and security requirements. However, these goals outline the typical requirements you should implement in every connected or non-connected device. The goals can be applied as required, for example, to an end-user connected device, a hardware component, a software component, or a service. We use the term device to represent any entity at any level that must be secure and trustworthy. The 10 security goals guide security design by covering the security foundations, allowing products and features to be developed on top while also providing a set of requirements the ecosystem can trust. Once implemented, products may go through a security evaluation, such as PSA Certified, to measure the robustness of the implementation. A user and the cloud both need to be able to trust a device. They need to know that the device hasn't been tampered with. They also need to know an attacker has not modified the device, and when accessing the device remotely, they need to know that something else isn't spoofing or pretending to be that device. A device needs to cryptographically authenticate itself and its code and data as it boots, and the cloud and the user need to be able to authenticate the device. For a user or cloud to interact with a particular device, it needs to have been assigned a unique identity, and this identity should be attestable. That attestation is then verifiable as a means of proving the device's identity. This identity facilitates trusted interaction with the device, for example, exchanging data and managing the device. Trusted digital device IDs can be securely stored in the roots of devices during manufacturing. Developers can build a unique identifier in each device, such as a serial number or key. For devices like smart cards and set-top boxes, this is usually achieved after board assembly at the personalization phase. Trusted credentials can defend against device cloning, data tampering, theft, or misuse. This identity is often placed into either dedicated security hardware, such as a secure element chip, or an isolated and trusted computing environment, such as a one-time programmable memory, or a trusted execution environment. This device ID is the very basis of a root of trust. Isolation of a trustworthy service from less trusted or untrusted services is essential to protect that service's integrity. More generally, isolation boundaries aim to prevent one service from compromising other services. For example, between any on-device services and between on-device services and the connected world. For devices running on the smallest embedded memories and the simplest architectures, there is a risk that the device's software will adopt a flat memory model, where all applications share the same privileges and resources. In a flat architecture model, any weaknesses, failure, or security breach in any application can impact all other applications, and therefore how the entire device functions. Some microcontrollers provide memory protection units and secure and non-secure regions, which allow for isolation. In smaller embedded systems, to increase the lifetime of a device, the designer can integrate a new application in the form of additional access controls. A designer should aim to minimize the amount of trusted code. Running more code in unprivileged mode increases partition isolation, thus improving reliability. There is sensitive data and system configurations that are critical to the integrity and security of a system and its operation. Keys to authenticate boot, to authenticate to the cloud, certificates, and so on. These all need to be secured and bound to the device to prevent disclosure beyond the system and their owner. To achieve this, we need secure storage that is only available to the trusted services that need them. Such storage should provide guarantees for confidentiality, integrity, and authenticity of the data which it stores. The key to a lot of the security goals mentioned in this module come down to cryptography. Without the use of cryptography, you cannot implement many other security features, such as secure boot, attestation, secure storage, and so on. Cryptographic authentication ensures that data exchange and handling is enabled only to authorized entities. This process uses cryptography based on secret keys and digital certificates to ensure that exchange data is coming from and delivered to trusted entities. As well as adding new features, software updates address known security issues. If a device can install previous versions of software, it opens up the risk of these known security issues being exploited. An anti-rollback mechanism should therefore be added to prevent this form of attack. This feature would ensure that new software versions invalidate older ones. Anti-rollback prevents exploitation of old vulnerabilities, which have been fixed in more recent versions of software or firmware. Security needs to be built to last as long as, or even longer, than the developed device. You may need to be able to stop someone from using a device that's been thrown away, building in a means to reset it or make it end of life. You may need to stop someone from being able to clone your device, rendering it useless unless it's been provisioned. You may need to ensure that unauthorized users cannot use a built-in debug feature to attack the device, building restrictions and controls to lock this feature out. Having a defined device lifecycle can help prevent such attacks. The security state of a device within its security lifecycle depends on software versions, runtime checks, hardware configuration, debug port status, and the product lifecycle phases. For robust long-term digital security, managing devices securely to minimize the attack surface throughout that lifecycle must not be overlooked. Security is not a one-off activity, but an evolving part of the IoT ecosystem that should support IoT development's lifecycle. As with traditional devices and software, the principle of regular software updates and password changes should also apply to IoT devices. Regularly updating firmware, exchanging digital keys or certificates, and other access policy managements are the bedrock of a strong security policy. Furthermore, the ability to react to evolving security threats and changing regulation is needed. If access is somehow compromised, such mechanisms will prevent future unauthorized access. When designing IoT devices, security lifecycle management solutions should be in place to meet these needs, with the ability to receive alerts and remotely address large-scale device groups, avoiding time-consuming and costly services in the field. Implementing a scalable security infrastructure at the design stage is essential against approaches that could expose IoT systems to damaging security attacks. An installed device needs to prove it can be trusted throughout its life. It can do this through attestation. As well as establishing their identity, attestation is required for some devices to prove their operational health, especially if they are the gatekeepers of secure networks, keeping an eye out for attacks. It is very difficult to determine if a device has been tampered with within your network in any IoT system deployed today. Therefore, it is necessary to authenticate the state of their code and data of any device that's on your IoT network. By definition, Attestation is a process between two parties, a prover and a verifier. The goal of attestation is for the prover to prove to a verifier that its operating system and application software, or both, are intact, up-to-date and trustworthy. The verifier trusts that attestation data is accurate because some form of certification key signs it. Attestation on its own cannot protect against malicious firmware modification, but can verify that a device is in a trusted state. Attestation can reliably tell a verifier what applications are running on a client machine. However, the verifier must still make the judgment about whether each given piece of software is trustworthy. Secure boot, sometimes referred to as trusted boot, and secure loading processes are necessary to ensure that only authorized software can be executed on the device. Secure boot ensures the system boots into a trusted configuration. Secure boot ensures the integrity of firmware and software running on a platform. It establishes a trust relationship between the device's initial boot code and the software it eventually launches, such as bootloaders, OSs, or drivers and utilities. After secure boot is enabled and configured, only attested software or firmware are allowed to execute. Conversely, software signed with blacklisted attestation is disallowed from executing. In this way, a system can guard against malicious attacks and unauthorized software updates before the OS or application code launches. Allowing unauthorized software is acceptable only if such software cannot compromise the device's security in any way. The secure boot mechanism relies on cryptographic signatures or other attestation techniques to verify the firmware before execution. If you cannot update a device's software easily, known vulnerabilities can be exploited, exposing the device and its data to attacks. Therefore, it is necessary to provide a secure means of updating the software. Manually updating IoT devices can be costly, making economic sense to provide this functionality remotely, providing its own set of security challenges, and opening up a potential attack surface. Developers, therefore, should ensure that vendor update and management processes follow best security practice. You should apply security patches and updates in a timely fashion without impacting the functioning of the device. Developers should ensure that the software firmware is created securely and signed to ensure the update's integrity. Developers should also ensure that the deliverable is protected by encryption to prevent the software image's exposure. Developers should ensure that only authenticated sources can provide security updates or patches. Allowing unauthenticated updates could enable attackers to find a way to run malicious code on the device. Devices and services must ensure the security of the image when sent and received. A device needs to validate the integrity of the encrypted update deliverable before decrypting the update. Users and managers should be able to see a device's patching update status through something like a remote management system. A device may announce the update for end users to approve the update installation. This step allows verification that devices are adherent to a specified security policy and ensures remedial action can be taken if required. Users should then verify the system is functioning appropriately. In conclusion, the 10 core security goals discussed in this module are embodied in the PSA Certified specifications designed to help you develop and deploy secure products. It is strongly recommended that all features are implemented. However, the features supported are determined by, for example, the intended application domain and cost, by any applicable national standards, by ecosystem operators, and by any certification scheme.